Welcome all to our first day of Equitable Growth 2022, People on Research Advancing Economic Evidence, and our second round of sessions. My name is Maryam Janani-Flores, and I am the Policy Director here at Equitable Growth. As you may have heard, this four-day conference brings together Equitable Growth grantees and other stakeholders to showcase cutting-edge research on how economic inequality affects economic growth and stability. Our session today is entitled Climate, Inequality, and Growth, and we have a number of great presentations ahead for you. The first paper presentation will be by Greg Casey, an assistant professor at Williams College, presenting his paper, Understanding Climate Damages, Consumption versus Investment. The paper adds heterogeneous climate change damages to investment and consumption models to understand the cost of climate change, and we're looking forward to hearing more. The next paper we have will be by Conor Walsh, an assistant professor at Columbia Business School, to present his paper, Clean Growth and Comparative Advantage. This paper uses a spatial growth model to assess the macroeconomic impact of the increased use in renewable resources. Derek Lemoine, an assistant professor at economics at the University of Arizona, will provide discussant remarks for both these papers. Next up, we'll have Jonathan Colmer, assistant professor at the University of Virginia, present his paper, Who Weathers the Storm? The Unequal Effects of Hurricanes in the United States, which looks at the distributional impacts of exposure to and consequences by hurricanes. Mark Curtis will then present our last paper. Mark is an associate professor at Wake Forest University and will present on his paper entitled Green Energy Jobs in the US. What are they and where are they? Which explores jobs in renewable energy and their characteristics like their location, education requirement, and their pay. The discussant for these two last papers is Eva Lyubich, research economist at the United States Census Bureau, who we are glad to welcome. We'll have about 10 minutes or so for each presentation and each discussant, and you may hear me interrupting remarks to keep time, only because it's hard to see chat reminders when you're in the middle of giving a great presentation. After all of our speakers, we will plan to open to audience questions and discussion, which I'll be moderating. One of the things that I enjoy the most about our grantee conference is the amount of participation that often happens during the Q&A session. I encourage you to submit questions into the Q&A box that you'll see on your screen on a rolling basis as they pop into your heads. And then I'll try to get to as many as possible during the Q&A at the end of our presentations. So when you're submitting a question, please include your name and affiliation so that you get the proper credit for your questions. You can also feel free to use the chat function if there are resources or thoughts you'd like to share with the full audience in real time. Lastly, I, like many of you, get very excited for each presentation in general when I attend these things. So as such, I'm going to drop a quick note in the chat about the tenor of participation we hope to see throughout the grantee conference. With that, I'm done with all my housekeeping remarks, and I'd love to pass it over to Greg for our first presentation.
Awesome. Thank you so much, and thank you for including our paper in the program. Can everyone see my screen okay?
Awesome. Looks great.
Awesome. So given the time constraints, I'll just jump right in. This is a paper thinking about how climate change will impact aggregate economic outcomes in the US. And we're going to focus on the role of construction. And to show you why we want to focus on construction, I'm going to start by showing you a picture of how the composition of the US economy has evolved over time. So like many developed economies, large shares of US value added come from services and manufacturing, which are relatively less vulnerable to changes in climate. And this is a major reason why developed economies are often thought to be less vulnerable than developing economies to changes in climate. But that doesn't mean that the US economy is completely invulnerable to changes in climate. In particular, climate change is likely to impact both the agricultural sector and the construction sector, in part because much of the work in these sectors happens outdoors. And so there's been a lot of great work thinking about how climate change will affect the agricultural sector in the US. And this is important work, but it's unlikely to be what drives aggregate outcomes. And that's because agriculture is a very small share of US value added, and that share has been declining over time. At the same time, construction makes up about 4% of value added in the US, And that share has been relatively constant over very long periods. So if we think about projecting these trends forward, we think that the vulnerability of the aggregate US economy is really going to be driven by this construction sector. And that sector has received relatively little attention in the existing literature. And when we think about trying to understand the impacts of construction on economic outcomes, it's going to be really important to distinguish between consumption and investment. So what I've done here is show you a picture that decomposes consumption and investment value added in the US for the year 2019. Just as a really quick reminder, consumption is when households purchase things for immediate use, think food and dry cleaning, whereas investment is purchasing goods or services now that are going to be used to produce output far in the future. So that's a lot of spending by businesses and also the purchases of homes by households. And in the US, the construction sector is really all about the creation and maintenance of structures. So really, when we think about climate impacts on construction in the US, we should be thinking about climate impacts on the investment side of the economy. And that's going to be important for reasons that I'll get to in just a few minutes. So what we want to do in this paper is build and quantify an economic model that respects this difference between consumption and investment and is therefore well suited for thinking about the impact of climate on the economy through construction. So obviously I don't have time to go through the entire model, so let me just give you a quick sketch. So there's going to be 3 final goods in our model, 1 consumption good and 2 different investment goods. One of those investment goods is going to be structures, and then we're going to lump everything else together and call that equipment. And these 3 final goods are going to be created with the value added from 4 underlying sectors: agriculture, manufacturing, services, and construction. And consistent with BEA data, we're going to have these first 3 sectors contribute to consumption, and they're also going to contribute to equipment investment. But then all 4 sectors, including construction, are going to contribute to the production of structures. And all this aggregation is going to happen with CES functions or generalizations thereof. And when we have this framework for thinking about the economy, there's really 2 ways that climate change can impact construction. The first is when we have changes in weather and climate, that is going to directly impact the productivity with which construction work can be completed. There's a lot of people working outside, and therefore they're going to be very vulnerable to changes in climate conditions. So I'm going to think about that as the supply of construction channel. And at the same time, climate change can lead to increases in either the frequency or the severity of storms. And those storms often destroy existing structures. And when existing structures get destroyed, that boosts the demand for construction relative to other sectors. So I'm going to think about that as a demand for construction channel. And what we want to do in this paper is use our model and existing empirical estimates to understand the impact of climate on economic outcomes through these 2 construction-based channels. Now, fair warning, we're still in the process of updating these numbers, so the precise numbers you're going to see here are still somewhat preliminary, but the aggregate economic takeaways are hold up sort of regardless of how we do this estimation. And so what I'm showing you here is the 2 types of damages that we're going to feed into our model. We're going to think about damages in a world where there isn't any large-scale efforts to implement climate policy. So that's sometimes called a business as usual scenario, or if you're familiar with these things, we're using RCP 8.5. And on the left, we're looking at that supply of construction channel. How do changes in weather and climate affect the productivity of the construction sector? And you can interpret this scale as sort of percentage. So, and really all these impacts are going to be dictated by extreme weather. So climate change shifts the distribution of weather, and it gives you more hot days, which reduce productivity in the construction sector. But it also gives you a reduction in the number of days below freezing, and that tends to increase construction productivity. So we're going to take the negative consequences of heat from the climate science literature and the benefits of fewer days below freezing from the construction management literature. And when we combine those with projections of future temperature, we get that climate change, or climate, I should say, extreme weather, reduces productivity in the US by about 3% today, relative to a world where you never had extreme temperature in either direction. That's going to be relatively constant as the sort of fewer freezing days essentially offset the number of really hot days. But eventually you get to a world where there's not that many more freezing days to get rid of, and this increase in extreme heat leads to a bigger impact of climate change, reducing construction productivity. So a little bit more than doubling from now to 2100. And on the right-hand side, we are thinking about the impact of storms on destroying structures. And these numbers are coming from my co-author Steffi Fried's recent paper in the Review of Economic Studies. You can interpret the scale on the left here. This is fraction of structures destroyed in 0.1%. And again, the climate impact is going to roughly double between now and 2100. So we're going to put both of these impacts through our model and then see what that implies for aggregate economic dynamics. And so our results are summarized by these two pictures here. And to start, I want to focus just on these solid lines, and I'll come back to the dashed ones in just a second. The solid lines are what our model predicts. And so everything here is going to be shown relative to a world where the climate stopped changing in 2019. So because we have climate change affecting both the stock of structures and also the ability of the economy to create new structures through the construction sector, we find that climate change reduces the capital stock by about 8.5 or 9% in 2150 relative to a world with no climate. And that reduction in the capital stock, that slowing of economic growth, is also going to make it harder for the economy to produce new consumption goods. And so even though the direct impacts are all through investment, climate change reduces consumption in the US by about 2.5% by 2150. And in existing literature, there are many different ways to quantify the aggregate impacts of climate change. Some of those completely ignore the impact of climate change on construction. So to a first approximation, you can think about these as being roughly additive to some other numbers that are out there, but that's going to depend precisely on what comparison you're doing. In my last minute or so, I just want to close by making one economic point that I think is important. The existing macro climate economy literature relies very heavily on what we call aggregate damage functions. And essentially what aggregate damage functions do is they take all the impacts of climate change and they smooth them over all the different sectors of the economy. So these dashed lines in this figure, this is what would happen if we tried to project the future impacts of climate through construction using these aggregate damage functions. And so in the US, we think a lot of these market damages are going to come from construction. And what the aggregate damage function is going to do is say, instead of having damages concentrated in investment, they're going to sort of be equally split between consumption and investment. So that means that these aggregate damage functions understate the impact of climate on investment, and they overstate the direct impact of climate on consumption. So on the left-hand side, we see here that if we sort of ignore the fact that climate is affecting investment more directly, we get a much smaller decrease in the capital stock. So in this sense, we think that standard models would be underestimating the impact of climate on economic growth. So this is about a 1.5% reduction versus 8.5 or 9. And consumption is a little bit more nuanced. In the short run, before there's really been much of a change in the capital stock, these aggregate damage functions are going to overstate the impact of climate on consumption because they have this bigger direct effect conditional on the size of the capital stock. But in the long run, after this change in the capital stock, this change in economic growth really starts to matter for how much consumption can be produced, these aggregate damage functions understate the long run impacts of climate change on consumption. So by using these aggregate damage functions, we think they understate impacts on capital, understate impacts on long run consumption, but perhaps overstate short run impacts on consumption. And with that, I think I'm out of time, so I'll just stop here on the conclusion slide. Thank you very much.
Thanks so much, Greg, and for keeping to time. You made my job easier. Next up, we have Conor Walsh presenting his paper, Clean Growth and Comparative Advantage. Conor, passing it to you.
Thanks a lot, and thanks for having me here. So this is joint work with Kostas Arkoulakis at Yale, and we are basically talking about the implications of the rise of renewable energy for global growth and regional outcomes. So the world has changed fairly dramatically in the last decade in that clean energy has now become very cheap. So the costs of wind and solar have fallen by around 80% in the last decade, and that is leading to a dramatic uptake in the installation of solar and wind capital across the globe from very, very low levels in the mid-2000s, basically nothing. And these cost reductions are projected to continue as output rises and capital costs continue to fall through both increasing economies of scale and learning by doing. So what we're doing in this paper is thinking about the global phenomenon of the rise of renewables. What are the macroeconomic and regional implications? And what's the role for policy in shaping this transition? So what we do in this paper is develop a spatial theory of clean growth, where we take very seriously the supply of energy and the transmission networks for trading energy across space at the regional and country levels. And electricity prices in our model are going to be set, as in the real world, by grid operators based on supply and demand. Demand in our model is going to come from a multi-sectoral trade model of production. And we're going to introduce into this setting a tractable theory of renewable investment that incorporates learning by doing, which seems to be very important for these renewable energy technologies. Once we got the model, we quantify it with pretty detailed regional data that we've collected that harmonizes data on the entire global power and transmission network, global clean and fossil energy resources and potential, and regional data on trade and production. And what we're asking in the paper is really, who are the winners and losers of clean growth? And what are the impacts of major interventions favoring renewables, such as the Inflation Reduction Act that we saw pass last month? So I'm going to give you a little flavor of the model. Obviously, with time, I can't go into too much detail, but basically thinking about spatial nodes in space. So you might think of commuting zones or NUTS-3 regions in Europe. These nodes are connected by an electricity transmission network. Electricity can be produced or used in any one of these nodes, and nodes can send or trade power from other nodes. As I said, demand is determined by a multi-sector trade spatial model with iceberg shipping costs. So you can think about industry, agriculture, services, they're all incorporated in demand for electricity. I'll discuss these and then I'll turn to specifying the model of renewables. But basically think about it like this, as a simple picture. You can have different nodes which both produce and use renewable and fossil energy, and you can have different industries using different amounts of electricity at different points in space. So we have data on basically all the fossil capital and renewable capital already installed in the world. This comes from the World Resources Institute, and it's available at a very fine geographic scale. So this picture just plots the distribution of fossil fuel capital and hydropower across the world. You can see it pretty much tracks population and industrial production, which is not quite true of renewable potential. So you might think in each one of these nodes, you could have a cost of generation, where that cost can be incurred from supplying fossil fuel derived electricity into the network with increasing marginal costs. So you burn some coal or burn some gas at your existing fossil fuel capital power stations. Each one of these power stations has a max rated output that you can't go above, at least in the short term. And electricity generated by renewables is going to look quite different in the model. They're going to be supplied at zero marginal cost, which is roughly true in the real world. So you set up a solar panel or a wind turbine in space, and with very little input of extra cost, you can generate electricity from this asset. And this is going to dictate how prices are set on the network. And the potential for renewables is obviously spatially varying. So there's some regions of the globe that are very good for supplying renewable electricity. So you've got the southwest of the US, for example, very, very sunny area, much less so in the northeast of the US. And interestingly, when you overlay the transmission network, say for a country like the US, it doesn't actually line up that well with current renewable potentials. So there's a bit of a spatial mismatch there in the transmission network in terms of getting electricity from where it will be very productive to produce it with renewables to where it's actually needed in sort of these heavy industrial areas on the East Coast. So on the left, I'm showing basically our harmonized data on the transmission network across different regions in North America, so also including Canada and Mexico there. There's some limited transmission capacity back and forth between the US and these two countries. And on the right, I'm showing you solar potential or renewable potential coming from the sun. And you can see that potential is very high in the Southwest, but that doesn't actually line up very well with the existing structure of the grid. And this is going to be key in determining how easy it is to transition to a renewable heavy grid. And wind power, a little different. Wind is very, very productive in the Midwest and basically straight down the center of the country, not so productive on the coasts. Now, I'll give you a flavor of the electricity utility planning problem, what they've got to do to schedule prices across space. They're going to think about maximizing industrial output over the regions that they control. So you might think about, say, an ISO or regional transmission organization that's setting prices across space. They're scheduling generation going into the network, both from fossil fuel assets and renewable assets, and they have to respect a bunch of constraints that become very important when you quantify the problem. So there's an energy balance constraint, basically demand plus the losses in the network have to equal supply onto the network. Losses are a function of both the structure of the network and the amount of net power put out in each node. It's basically a quadratic form. And then the planner also has to respect two constraints. So there's a max output that they can put into the network at each point, and there's a maximum line output. So they can't run the electricity network too hot down certain lines or the lines will burn out. And the planner has to take that as given, and they set prices to solve this problem. So they do that statically, and then dynamically, there's an investment module going on where private entrepreneurs and capital will basically think about setting up new solar capital and new wind capital at different points on the network. So how does that work? Well, there's a simple law of accumulation of renewable capital. So it's a dynamic accumulation equation where capital depreciates at some rate determined by how quickly solar panels and wind turbines wear out. There's some investment QJ, and that QJ is really the heart of how the model operates. We're going to have a global learning by doing spillover in that the cost of producing solar and wind capital is declining through time as aggregate output of these assets increases. So as we learn to produce these assets better, the installed cost will decline. And so we're going to fit this to actual data on project costs for both solar and wind capital. You see for solar, the price declines are quite dramatic. So as total installed capacity at the world level has gone up, the price has gone down quite dramatically. And we're going to fit this law into the model and think about its implications for driving decarbonization. Now, the renewable technology is quite different to fossil fuel capital. It's modular, meaning that you can set up plants of different sizes at roughly linear cost. And as I said before, it has zero marginal cost of supplying the network. That means you're going to have a very tractable free entry equation into each location. And that's what basically makes the model easy to solve. So in the time remaining, I'm just going to go over briefly some results and then I'll stop. But basically, we're going to quantify, as I said, with data on pretty much the entire global power network and renewable potential across space. And so we basically think about two key counterfactuals in the paper. We'll think about a baseline case where renewables aren't subsidized and the only thing going on are these aggregate spillovers at the global level from learning by doing and producing these new capital types. We'll solve the transitional dynamics with perfect foresight and think about who wins and who loses. You can see the baseline transition here. Europe transitions to renewables very, very fast, generally because they have high power prices, even before thinking about the conditions from the war this year. The US is not far behind. China takes quite a bit longer to transition to a decarbonized grid in our model, because their power prices tend to be quite a bit lower. They have very, very cheap coal, and they're still building significant sources of fossil fuel capital. The costs of solar power and wind power continue to fall on this transition path. We project that by 2030, costs come down another sort of 60, 70% relative to where they are today. And there are large welfare gains across the globe just from cheaper power. So here I'm plotting some of the welfare gains from different countries. They're sort of in the 5 to 10% range, which is quite large when you think about the cost of climate change. Different models give you different answers. So Greg gave us one, but you might think about costs of climate change being in the range from sort of 2 to 10%. This will say that renewable capital and cheap power acts to at least partially offset a lot of these costs coming from the direct externality of climate change. And then we think very briefly about different policies in terms of managing this transition. So think about the Inflation Reduction Act signed into law by President Biden. A key component of this was a production tax credit to renewable energy of $26 per megawatt hour. We can model this quite easily as a subsidy to production in the model and think about what it means, phases out by 2034. And what you get is that it does actually increase the uptake of renewable energy in the United States quite substantially. So instead of reaching 60% of the grid renewable by 2030, we actually get somewhat closer to 80%. But a lot of this subsidizes inframarginal investment. So we have the total cost of the bill being something like $700 billion, which is a couple of multiples of what is actually projected. And a lot of this is because it's going to subsidize investment that is basically already going to take place even in the baseline case. So that's all I've got to say. There are obviously spillovers to the rest of the world. The US decarbonizing spills over onto Europe and China and modestly speeds up decarbonization elsewhere. We think there's a lot of interesting things to go ahead with, and we're looking at grid investment next. But basically the upshot is cheap power is coming, and there are going to be a lot of benefits from this renewable transition. Thanks a lot.
Thanks so much, Conor. I would love to pass it on to Derek Lemoine, who will provide discussion remarks for the last two papers.
Great, thank you. And thank you for the invitation. Happy to be here. Definitely papers, both very different, but also similar in some ways. So both papers are really about investment and climate change. This much is probably pretty obvious from the 10-minute talks. Climate change impacts investment. That's the first paper. Second paper, how do we invest in renewable energy, presumably because we're concerned about dealing with climate change. So I'll start with the first paper, Greg's paper. So what they're trying to do is break open this black box of damages. And there's been, I think most environmental economists, maybe all, recognize that these damage functions are a critical part of these models. They define the social cost of emissions, but they've largely been not empirically grounded. And here the point is that even the form of the damage function might not be empirically grounded. So traditionally, we see warming, temperature, T sub T in this notation, causing some sort of damages D that are typically a quadratic or something like that in temperature, that just takes, you just lose a share of the economic pie right off. And you lose a bigger fraction of the pie, the worse climate change is. And then you have the rest of the pie remaining, you allocate that as you want to consumption, investment, emission reductions, whatever. And then the next period, again, you lose a share of the pie based on warming and so on. But the point of this paper, or the kind of founding observation of this paper, is that there are important sectors that are really exposed to heat. And those sectors are important not just for the size of the pie coming out, but for the size of the oven that you have in subsequent periods. They're really sectors that are about capital investment, not about consumption within a given period. And they also observe, I think here the empirical evidence isn't quite as strong as the paper shows. I think it's actually mixed. I've seen work on China that suggests the opposite, but they do suggest that manufacturing might be relatively robust. So it may even be that most of the damages are about the size of the oven you have in subsequent periods, not about the size of the pie you bake with a given oven. So here what they're going to do is disaggregate damages, break open this black box to have damages to investment and to consumption or consumption goods. They're going to creatively calibrate it to literature and heat stress and to the work on structural damages as well. And then the upshot really is just the long run effects of climate change are a lot worse if you think that we're going to have a smaller capital stock. That'd be sort of what I would take as the main takeaway of the paper. So I like the point very much. I mean, obviously the damage form that we've used is fairly ad hoc and pretty reduced form. I think breaking that open is really important. And I like the way they broke it open. It's not as purely a black box macro specification. It's also not as purely reduced form and atheoretical as a lot of empirical work. So they're trying to thread the needle between these, and I really appreciate that. I think I'll stick to 2 comments, given that there's another paper to talk about. So first comment is I think they can inform a wider debate. I understand that they don't like aggregate damage functions, but they are useful for lots of types of modeling one might do. And so I'd like to know what the right form of that should be. In particular, there has been debate about whether damages should come out of the level of output or of the growth rate of output. The conventional wisdom has been that growth rate damages yield way higher damages and way higher carbon taxes. That seems to me like it depends on the calibration. It's never seemed to me to be intrinsic, but that's at least the way a lot of people think about it. But these growth rate damages really haven't been analyzed much with microfounded models, and like growth rates aren't primitive objects in these models, right? Growth arises because of R&D investment or here capital investment. And so the authors are getting close to actually doing a microfounded analysis of growth rate versus level damages. So I'd like to see them take that through all the way, like fit the reduced form damage specifications to their output. What would level damages look like? What would the best fitting growth rate damages look like? What's the best fitting mix of the two? It would help us understand which is better, the right magnitude of growth rate damages, because I have a feeling we've been using way too large specifications when papers do use them, and how close more reduced models can't even get to a microfounded model. Maybe you find that you could fit it pretty well with the right specification. Maybe you find it's hopeless and you need a microfounded model. I don't know what you'd find, and I'd like to know. And then ideally, give us a better aggregate damage function. Give us something we can use in a model that tells us the optimal carbon tax and that we could do analytic work with, et cetera. The other comment is I wonder if they missed the hook. I don't know if I missed it in the paper. Or I don't understand why we don't know the social cost of carbon implied by their model. I understand they might not want to optimize the carbon tax, but just tell us the social cost of carbon. It seems like a trivial amount of work on top of the results they have, and it's the number that we think in terms of. It seems like the paper is really selling itself short without doing that, and I'm just really confused why it's not in there. So what I'd love to really see is a curve of the social cost of carbon, a plot with several curves. X-axis is discount rates, and then a curve for the social cost of carbon from their model, a curve from the dice-like model. So this is the analog to the graphs that they were showing, and then curves with models fitted where they try to take the best aggregate damage function as fitted to their results, as I suggested in the previous slide. And then we'll see how the low discount rates make the social cost of carbon a lot higher with their model, and we would see how close the fitted models might be able to get. It would just make their work a lot more useful for the profession, I think. For the other paper, Arkalakis and Walsh paper, here we're really trying to take the spatial aspects of electricity grids seriously in a macro model, and I think that's a really valuable contribution. There's a long tradition of very detailed electric power systems modeling in the energy IO literature, and more of that should be cited here. I understand it's a preliminary draft. I don't know of theory-driven macro models that are calibrated in more of like a theory-driven sense that have really taken the structure of the electric grid seriously. So this paper seems to me to be at the frontier in doing that. I do want to caution, though, there are lots of energy economy integrated assessment models, especially the cost effectiveness models, not the kind that Greg and they were discussing in the previous paper, that are all about taking electric grid seriously. And they have ways of representing intermittency and investment and all that kind of stuff. And so there's a real contribution here. It's a very different kind of modeling project they're engaged in, but they should be touching on that literature and definitely acknowledging that it's out there and clarifying the similarities and differences to it. I do like the representation. It's clever, tractable, interdisciplinary. It matches what I remember from my electric power systems classes. I don't remember everything though, so I haven't checked it, but I love seeing reactive power in an economic model. They use novel data from OpenStreetMap that seemed clever. So I like all this a lot. There's a lot for me and for many other papers to learn from. My comments are, first, the model feels a bit rigged. So all of those things I mentioned are really good, but then I wonder whether the results are really a bit predetermined. So there's no fossil fuel investment, which automatically makes the projections of renewable energy growth feel a little bit like that kind of had to happen because we had to have energy. I know it's not quite that simple, but having a competing investment option seems pretty critical. Then the fossil fuel they do have is calibrated to oil. And oil is definitely not the fossil fuel I would have picked. I mean, primarily electric generation is coming from natural gas and coal around the world. There's some oil use in some parts of the world, but in a lot of the developed world, it's not the first fuel we think of. It would be the third fuel at best that we would think of. And then on top of that, there's no real intermittency. They do try to address intermittency, but I'd really call what they're doing variability. It's the predictable seasonal and day-night shifts in solar electricity. It's not the minute-to-minute stochasticity that we call intermittency. And my annual review of resource econ paper on solar goes into this in detail and talks about the way that competing aggregated models, the ones I mentioned on the previous slide, do try to actually approximate intermittency without being able to get into the nitty-gritty. And I think it's important to both be clear about the difference and try to bring some intermittency in because it's critical to the solar problem. And it makes fossil fuels more important without a battery. And they also, the variability they do have, they kind of assume away in a way that's not entirely satisfactory. I think they need to take this a little more head on. Finally, learning by doing is also a bit rigged. It's a really extreme form of learning by doing, where there's a calibration that basically attributes all observed improvement in renewable energy costs to learning by doing. In reality, there's directed research, there's chance, there's reverse causality where we invested more because we saw costs were falling. And any one of these things, I think, would mitigate the level of learning by doing they detect. So we really need some bounding exercises where we shut the channel off entirely. We use a more moderated form. We use the extreme form. I mean, theirs is really a corner solution, I think, in one direction. So the model seems fated to predict higher renewable penetration. And it's not clear to me how much transmission is going to matter. If renewables are that dirt cheap, there's not another good option, and there's no intermittency, then you're going to just build out renewables one way or the other. So I think the authors need to weaken these assumptions a bit. Related to that, again, I understand it's an early stage project, but that also means maybe this is a good chance to say this. The main contribution is in the electric power system side on taking the spatial aspect seriously. So here, I think they can design better counterfactuals. So I would really like them to focus on the fact that transmission is their contribution and really design experiments that highlight the value of better transmission links. In particular, what they do better than a lot of the Energy IO literature is that they're thinking about links across countries, not links within small regions or across regions in the United States. They've got US, Mexico, Africa, Europe, Asia. I mean, it's a really remarkable data set of transmission. And just understanding the scope for moving renewable energy around the world, not just around small regions, would really be, it is fundamentally a macro question. It's a trade model with all kinds of weird distortions in regulated markets and just pipeline distortions. And we don't know the answer. I don't think anybody's really looked at that in an economic way. I mean, I'm sure engineers have, but I don't know that economists have. And that would be huge value added to do that well. These are policy relevant questions I just simply think could not be answered well without this framework. And that's really where I'd like to push them. Last, on both papers, and both of them, capital investment is really where growth is coming from. I really wonder, what about R&D? I mean, that would be the more modern formulation of the source of economic growth. And not that one paper needs to do everything, but at least as a discussion in both of them at minimum. So in the first paper, if there are R&D, does that undercut the importance of damaging investment productivity? It seems like now there's another way to get growth. So turning that off kind of maximizes the importance of investment damages. In the second paper, if renewables are being driven by R&D as well as by learning by doing, or even instead of learning by doing, then how does transmission constraints work? So you can imagine that now, if you anticipate transmission constraints, R&D might be forward-looking, and you might get less investment in renewables, and you might not see the cost declines that you would see if you took transmission constraints away. Or alternately, if R&D is in the transmission side, whether you want to think of batteries substituting for transmission or better forms like high voltage DC, then in that case, you might imagine R&D is actually directly working to make the grid more redundant in a sense, like to overcome the inability to build new lines. So you can imagine a counterfactual that compared a successful payoff of R&D to make transmission lines less necessary to a counterfactual that might just have a much better grid with existing technology. And you might be able to compare these two things, and that could be interesting. So thank you. Those are all my comments. Thank you for the interesting papers. Thank you for the 15 minutes, and I look forward to the Q&A.
And thank you, Derek. Appreciate your comments. And while I would love to go into discussion and hear some of the authors' thoughts on your comments, my job is to move us forward. We'll hopefully have some time at the end for that. So next up, we have Jonathan Colmer on his paper, Who Weathers the Storm, the Unequal Effects of Hurricanes in the United States.
Great. Thank you for having me, and thank you everyone for coming today. This is great to speak to you all about this work, which is, to caveat, still ongoing, but we're very grateful to the Washington Center for Equitable Growth for their support in the work that we've done so far. So this is joint work with my longstanding collaborator, John Voorhees, a principal economist at the US Census Bureau, and Brennan Williams, who was at the University of Virginia, now at the US GAO. And this is part of a broader research agenda that John and I have been engaging in as part of the Environmental Inequality Lab, trying to provide more systematic and comprehensive evidence on the distribution of environmental risk in the United States to better understand who's exposed as well as the consequences of exposure. And this sort of comes really from a perspective of noting that, we see that there are these patterns, these well-established patterns that disadvantaged communities are disproportionately exposed to environmental risks. And we see also broader patterns of economic inequality that have evolved in recent decades. And so wanting to understand, our core motive is really wanting to understand the degree to which environmental risks might contribute to broader patterns of economic opportunity and inequality in the United States. And we have a lot of sort of micro level estimates that have been well identified to look at the effects of temperature and pollution and natural disasters, but less evidence on how these things sort of add up. And one area that's been particularly difficult to try and understand is really understanding the distributional consequences of environmental risks. So while we know that there are disparities in exposure, understanding the degree to which different groups are differentially affected by the same sort of shocks and risks is much less understood. And so, when we combine the potential for disproportionate exposure and disproportionate consequences, this can amplify the degree to which environmental risks could exacerbate existing inequalities. And so the way that we have been sort of approaching this has been to basically be constructing a very large microdata infrastructure for the United States to help us to move from sort of place-based to a person-based understanding of environmental inequality. So what does this mean? Well, we've basically put together a data set at this point, which is the near universe of the United States. So it's all legal residents in the United States. And we have constructed fine level residential histories for each individual, as well as employer-employee linkages, which allows us to track individuals over time and space and employer. And combining this with high resolution data on environmental risks, which has increasingly become available due to advances in computational science, as well as advances in atmospheric science and other areas of environmental science, we're able to sort of get to the individual level of understanding what's the causes and consequences of environmental inequality are. And so the broad question we want to understand is, how this level of detail changes our understanding of exposure to environmental risks and their consequences. Now, in the context of this project, we're combining spatially continuous data on hurricane exposure with individual level tax and demographic data to produce new facts on both distribution of exposure as well as the distributional consequences of hurricanes. And sort of at a higher level, we're using hurricanes because we're interested in understanding the consequences of hurricanes, but we're also interested in using hurricanes as a means to an end. A lot of the existing work on trying to understand local economic shocks has, as well as the literature on hurricanes, has sort of given us detailed information on what the average effects are, but the average effects don't necessarily tell us the whole story. We want to understand the distributional consequences too. And so there are 3 parts to the project. I'm going to focus on parts 2 and 3 today, but the first part is to provide sort of new stylized facts about hurricane risk and experience at the individual level. And what we observe is that on average, there hasn't been any systematic movement away from or towards riskier areas in the last 2 decades. And so exposure has remained sort of relatively constant. And that lower income and non-Hispanic, Black and Hispanic individuals are disproportionately exposed to hurricane risk. And so whereas you might think that it's just rich people living in mansions on the coast, that sort of prior is not consistent with what we observe in the individual data. So second part is to understand the dynamic effects of hurricane exposure on total income, on earnings and transfers. We're doing also work to better understand responses as well in terms of migration and other margins, but today we'll just focus on total income, earnings and transfers. And then we're going to understand how individuals exposed to the same shock are differentially affected along the margins of race, income, as well as race-specific income differences. And so that's one of the advantages about moving from a place-based to a person-based understanding of these effects, is that we are able to understand differences and effects within race-specific income distributions. So the data comes, as I sort of mentioned, the data we're going to be using today for our core sample frame is the 2000 long-form census. We're building on the infrastructure we've been developing to result in a larger sample. But we basically take these individuals and we construct a panel data using tax data from the IRS to then get at sort of exposure at the census tract year level, as well as then being able to understand the consequences on various outcomes. So we combine this with what we would describe as exogenous physical measures of maximum sustained wind speeds and dissipated energy, rather than focusing on damages, which are more endogenous to the location's economic and political situation. And so altogether, we end up with this panel data information on exposure combined with individual level information on these various margins of earnings and income and transfers. We're going to focus on the 21 hurricane states of the United States, looking particularly on coastal counties and those who are aged between 25 and 64, although these restrictions don't really make a huge difference to our outcomes. So this is just the distribution of maximum sustained wind speeds in the United States. And it's worth noting at this point that a large part of the existing literature has tended to focus on individual storms like Hurricane Katrina or Hurricane Andrew. And that's tended to mean that our understanding of the consequences of hurricanes are more disproportionately focused on the extreme events, rather than getting a better understanding of how hurricanes overall affect economic outcomes. So in terms of understanding the effects of hurricanes, we're going to be focusing on a sort of panel data local projections estimator. An applied micro approach to thinking about the effects of hurricanes might naturally move towards thinking about a difference in differences type setup. We argue that it's not really appropriate in this context because exposure is non-binary, it's a transitory shock. There are repeat events and exposure timing is staggered. And so because of this, that raises a number of econometric problems that we think are not really conducive to doing the analysis we're interested in. Instead, we are focusing on trying to understand the effects of these shocks rather than sort of imposing a data generating process, which is sort of constant. A solution in the literature has been to sort of focus on one storm or focus on the first event. But instead, we're drawing on insights from a recent paper by Basso, Miller, and Schaller that argue that the local projections estimator, which comes from the macroeconometrics literature, is the most consistent estimator for repeat transitory shocks under the assumption of conditional independence. And we think that assumption is reasonable in this context because the number of hurricanes that form, where they form, the path, and all those considerations are plausibly exogenous, conditional on location and time fixed effects. And so instead of a sort of parallel trends assumption, we're relying on conditional independence, which in this context we think is reasonable. So just to give you an overview of the results, what we find is that on average, exposure to sort of 70-mile-per-hour winds, sustained winds, which is sort of the median event in the sample, is associated with small reductions in total income, about a 0.3% reduction in total income. So these are small effects overall. This is sort of within individual, using individual fixed effects and state year time fixed effects, or state year fixed effects. So on average, the effects, we do see a reduction, but those are very small reductions. When we look at earnings, we see a bit more of a response, about 0.6% reduction in earnings. And again, the effects are sort of relatively short-lived. We see an initial reduction relative to the year prior to the hurricane, and then sort of a return to trend within a year or two. And the reason that the total income effects are more sort of offset is because we also see increases in what we're calling transfer income, which are these sort of immediate increases. And then interestingly, we see over time that these effects sort of decrease and become negative. Now, this is potentially consistent with the work that Matt Kahn and Rhiannon Jurch and others have done, sort of looking at the local public finance consequences of hurricanes. And so the sort of immediate effect of the hurricane is to increase transfers, but if there are reduced taxable income in the local economy, that might have consequences for the availability of transfers later down the line. But overall, consistent with the existing sort of aggregate literature, it seems to be the case that the average effects of hurricanes are relatively small, and that individuals seem to be reasonably well insured against the effects of hurricanes. That being said, the distributional effects look different. So we see that in terms of margins of race, we see much larger reductions and longer returns to trend in total income, so not just earnings, but total income for non-Hispanic, Black, and Hispanic workers. If we look at sort of unconditional quantile regressions, recentered influence functions, we see that losses are concentrated and higher in the bottom 30% of the earnings distribution, the total income distribution. And if we look at race-specific income effects, we see that these reductions in the bottom 30% are concentrated specifically among Black and non-Hispanic, Black, and Hispanic workers. So the effects are much larger and disproportionately focused on lower income Hispanic, non-Hispanic, Black, and Hispanic workers. And so the average effects are masking this heterogeneity. So just to conclude it with some contributions, I think we contribute to the broader literature on the economic consequences of hurricanes by sort of looking at moving to an individual level understanding and focusing on trying to understand sort of the overall effects of hurricanes and their distributional effects, not just focusing on one particular storm, and trying to understand not just the contemporaneous effects of hurricanes, but dynamic causal effects. And I think one of the key take-homes of this in terms of within the local economic shocks literature is the need to understand the distributional effects. If we just look at what happens on average, then we might draw conclusions that suggest that the population is reasonably well insured, and that is true if you are middle income and white, but is not necessarily the case. In fact, we see not the case for lower income groups, particularly lower income non-Hispanic, Black, and Hispanic workers. Within the literature on race inequality and environmental inequality as well, we make contributions in terms of the data that we have been producing. Existing work on administrative data tends not to provide information on race because the IRS doesn't have that information, or it tends to be based on surveys, which are smaller samples, which makes understanding these effects a lot more challenging to do for power reasons. By focusing on people combined with this data, we're able to provide new insights to suggest that these pre-existing racial disparities in climate risk that we see combined with larger losses could be contributing and exacerbating contemporary racial economic disparities. So thank you for your time.
Thank you so much, Jonathan. For our last presentation, we'll have Mark Curtis presenting on green energy jobs in the US. What are they and where are they?
All right, thank you so much for having me. This is joint work with Ioana Marinescu, who's at the University of Pennsylvania. So the question is pretty simple, and this is a pretty straightforward paper. So what we're going to try to do in this paper is to really understand green energy jobs in the United States. We're going to use some new data to try to understand where these jobs are located and some of the important characteristics about these jobs. So we are in the United States very quickly transitioning away from fossil fuels and to renewables. The amount of renewable energy production is dramatically rising and is expected to continue to do so, certainly with the Inflation Reduction Act having been passed. And so what we want to do is try to understand what this transition means for workers in the United States. We'd like to gain some insights into what types of jobs are created from renewables and think about how policies like the Inflation Reduction Act is going to affect workers and communities. So, this has been a big political issue. So, a huge part of the Inflation Reduction Act was trying to ensure that jobs were going to be located here in the United States, that the future green jobs were going to be located in the United States. And there's a number of reasons for that. And I think first and foremost is likely the political support that can come when you have a large job base that's in a particular area of a policy that has been passed. So I also think that the support for future policies, future environmental policies, climate change policies, is likely going to be determined in large part based on the benefits that are going to accrue to workers. And if we see large benefits to workers, then I think we're going to see more. It's going to be much more likely that we will see support for future climate change policy. So, we want to know about these jobs. We want to know about what sorts of workers are in solar and wind industries. But there is a lot of challenges to overcome with this. So you might think this would be a straightforward question, but it's not. So the traditional industry and occupational codes that we have used to measure jobs in the United States do not have solar and wind jobs, right? These are types of jobs that typically fit within other sorts of well-defined categories. And so we don't actually have much information on workers that are directly interacting with solar and wind energy. So just as an example, solar panel installers tend to be classified as electricians. Wind turbine builders might be classified as construction workers. And so actually getting a number and identifying these workers is particularly challenging with the existing data that we have here. And so what we really need to identify these workers and to understand some of the characteristics of these workers is the detailed descriptions of what these workers are actually doing. And so in order to get some detailed descriptions of what workers are doing, we're going to turn to online job postings, specifically Burning Glass data, which is now Burning Glass has changed names to Lightcast now. And we're going to take nearly the 1 billion online job postings from online job postings, and we're going to essentially search through these job postings to try to find particular keywords that's going to allow us to identify these workers. So we're going to look for keywords like solar, photovoltaic, wind, and then we're going to be able to look directly at the job titles, the task that these workers are actually doing in their job, and their employer to be able to pick out which workers are engaged with renewable energy types of activity. And so that's going to be the key contribution. Is really just of this paper is to really just identify the workers that are interacting with solar and wind energy as parts of their jobs using very detailed online job postings. Okay, so once we've done that, and I will spare you all the details of how we do that, certainly for this presentation, we're going to be able to look and see exactly what occupations these workers are in, what industries these workers are in. We're going to be able to observe where these workers are located, and more characteristics. We're going to ask if the jobs that are created in these in solar and wind are going to be high-paying jobs. And then if so, we're going to ask, so for whom? So which workers are going to really be benefiting from these new jobs? And then finally, we're going to be able to examine some of the characteristics of the communities where these jobs are in fact found. Okay, so getting kind of straight to the results. So this is a simple time series looking at the number of job postings in solar and wind jobs that we identified in the Burning Glass data. So Burning Glass starts in 2007. There's a couple of years that are missing, and then it picks back up again in 2010. And so we see that between 2010 and 2019, job postings in solar and wind jobs, as we have identified them, are more than tripling over this time period. By 2019, we're seeing about 52,000 solar job postings and about 13,000 wind job postings. Again, these are job postings, not necessarily job levels here, but this is the job posting data that we have. So large increases in time, and even some of these bumps that you see right here. So for example, the drop in 2016, 2017 is in fact consistent with what we see in a drop in new solar installations in the United States. So we feel pretty confident that this data is actually picking up a lot of the trends over time. Okay, so occupationally, where are these jobs located? So the big thing that I'll point out here is that the top one. So this is kind of comparing the percent of jobs in solar that are in, traditionally what we might call blue collar occupations. So if you look at wind, so about 50%, that's the bar that is furthest to the right on your screen, the yellow bar there. So about 50% of wind jobs are located in what we might define as blue collar industries. And if we look at solar jobs, which are in green here, and you look at the bottom sales, the bottom sales portion, we see that about 32% of jobs that we identify as solar are in sales occupations, relative to only 11% of the overall economy. Okay, so wind jobs are more likely to be in blue collar occupations. Solar jobs are far more likely to be in sales. We can kind of even dig a little bit deeper into the occupational breakdowns of these jobs. So, wind jobs are really in installation and maintenance that we're identifying. Again, we see solar jobs as being highly represented within sales occupations. In terms of industry breakdowns, we see that wind jobs tend to be in manufacturing and professional and scientific industries. And we see a lot of wind jobs in particular in these really big conglomerates like GE and Siemens, which kind of confirms the fact that we really need a really detailed understanding of the job posting, right, to be able to identify the wind and solar workers within these really big conglomerates. And so we see a big amount in manufacturing for wind, and solar jobs are, the most prevalent industries are utilities and construction. Okay. So for the education requirement breakdown, so each job posting is going to list its education requirements. I think the big thing here is that we see that solar, a lot of solar jobs do not list an education requirement. So if you look on the right side screen, 62% of jobs do not actually request any sort of educational requirement for solar. All right, so quickly moving on, are green jobs high paying? So what we're going to do is we're going to, for every single job, wind and solar job, we're going to assign that job to have the median earnings of its 6-digit occupation. And then we're going to do some pretty straightforward regressions on solar and wind job indicators. We're going to be able to control for things like the median education requirement of the occupation. We're going to control for the location of the job, and we're going to really look within broad 2-digit SO categories. So we're going to look at two. You can think about having two construction workers. One is in either solar or wind and the other is not. And then we're going to be able to say, okay, what do the earnings look like for the solar and wind jobs relative to other construction workers who are not in either solar or wind jobs? And just kind of quickly getting to it. So we see that there's roughly a solar wage premium of about 15 to 20%. And we find a wind wage premium of around 4 to 16%. And this premium, importantly, is largest for the lowest education type jobs. So we see a 30 to 33% premium for high school workers in solar, for example, and only a 5 to 10% premium in solar for college workers. So where are these jobs located? This map is going to look very similar to one that you just saw a couple presentations ago. So this is kind of confirming that we feel like we're doing a pretty good job identifying these. So solar jobs, are mostly in the south and southwest, with a few in the northeast, and wind jobs are kind of right smack in the middle of the country where you might expect them to be. And so we can take this information from where the percentage of job postings in a commuting zone, and we can say, okay, so what are the characteristics of these communities where we observe solar and wind jobs? And so we can ask, so are they located near manufacturing jobs? And the answer is actually a pretty definitive no. So solar and wind jobs are not located near manufacturing jobs. But they are in fact located near fossil fuel jobs, right? So jobs that especially like mining for fossil fuel, oil especially, we do see a fair bit of overlap between the percentage of jobs in a CV that are solar and wind and the percentage of jobs in a commuting zone that are fossil fuel type jobs, suggesting that there might be some ease of transition between fossil fuel jobs, particularly in oil, and those in solar and wind. All right, so just to kind of wrap up, so we use new data on job vacancies with solar and wind job skills from burning glass technologies. We see green energy jobs are certainly not homogeneous. Solar jobs are currently disproportionately in sales. Wind jobs are disproportionately in blue collar occupations. Green energy jobs are created in occupations that pay about 20% higher wages. And the pay premium is highest for jobs requiring less formal education. And we also see that green energy jobs are disproportionately located in labor markets reliant on fossil fuel employment. So we think this has big implications, particularly for the Inflation Reduction Act, and which is actually trying to get even more of these sorts of green jobs located in the United States, especially more in, you can think like solar manufacturing, right? Where we actually don't see a lot of solar manufacturing jobs. But that's been one of the big focuses of the Inflation Reduction Act, is to try to get more of those types of manufacturing jobs located in the United States. So I will finish there. Thank you.
Thanks so much, Mark. Last up, we have Eva Lyubich, who's going to take us home as discussant for the previous two papers.
Awesome. I will share my screen as soon as, Mark, I think you have to, oh, I can stop. Here we go. All right. Thank you to everyone for being here and to the organizers for asking me to discuss these two excellent papers. I need to include a disclaimer that all opinions and conclusions I say today are mine and do not reflect the views of my employer, the Census Bureau. I want to begin by sort of taking a really big picture step back about like why I think these papers matter and sort of how to think about the motivation for them, which is that global average temperatures have increased by over 1 degree Celsius or over 1.8 degrees Fahrenheit from pre-industrial levels up to 2022. And so addressing climate change is going to sort of very broadly speaking involve two categories of actions. The first of these is addressing the consequences of the consequences that of climate change that have already been baked in from past and ongoing emissions. And the second is avoiding even worse consequences by as quickly as possible transitioning the energy system away from fossil fuels. And in both cases, these consequences are going to be unevenly distributed across the population. And they're also going to sort of involve a spatial component to the uneven distribution because of the nature of natural disasters and energy production and consumption. And so, for policymakers who care about addressing climate change in an equitable and just way, understanding these distributions is going to be really important. And each of the two papers that I'm discussing today makes progress on one side of this coin. And so that's very exciting. Let me begin by talking about hurricanes. So just a little bit more context, storm damages have been increasing over time and are expected to continue to do so as climate change intensifies storms. The green bars here are the number of billion-dollar hurricanes each year, and you can see that those have been increasing quite dramatically. And then it's also sort of been well documented that storm impacts are unequally distributed. So here's a couple of headlines from the Washington Post and E&E News, sort of showcasing and speaking to this point. And so clearly it's going to be sort of important to understand heterogeneous marginal damages from hurricanes. But being precise about what those marginal damages are and why they differ across populations is hard for a couple of reasons. So first of all, one reason is that we typically talk about storm strength in terms of dollar damages or number of deaths, but these are endogenous measures. And as a somewhat aside, I think thinking about storms in terms of cost damages can make it really difficult to think about distributional damages because we would sort of treat as equally damaging a storm that destroys one $10 million home versus $50,000 to $100,000 homes. But obviously the distributional impacts there are very different. But then additionally, a point that Jonathan and co-authors make in their paper is that marginal damages are sort of reflect a combination of differences in exposure to a risk and then differences in consequences of the exposure to the risk. And it's sort of difficult to measure variation in those two things across population groups separately in different groups, but in standard data sources. But I think, just to emphasize this point, this figure from Saul Sheng and Al's co-op paper from a couple of years ago, I think really highlights how, when you look at damages to two different groups that face different exposures, it's hard to know whether the damages that they face are different because they're at different points on the same nonlinear damage function or because they have different marginal damage functions. But sort of from a policy perspective, understanding those differences is really important. And so this paper is going to take these challenges seriously and sort of use awesome new data and a panel data approach for estimating treatment effects of repeat transitory shocks to bring new evidence on heterogeneous treatment effects to light. And so in particular, they're going to be using measures of exposure to wind speeds as their measure of exposure to an environmental risk. And so they address some of these issues around sort of measuring exposure. And then because they're able to build a panel of individuals who living in different places across time, and they're able to sort of observe individual demographic characteristics and economic outcomes pre and post storm exposure, they're able to sort of really dig into some of the issues around how much of marginal damages are differing due to exposures or due to differential consequences. I'm not going to summarize the results. You've heard them all recently enough, and I'll just get straight into some of my suggestions. So my first set of suggestions is just that, like, this is a really exciting context, and so I want to see more descriptive results, and I'm sure that you will have more descriptive results in the paper as you sort of keep making progress on it. But a few questions that I had just sort of looking through your slides this go around were, so you highlighted one result that there's not systematic movement to and from risky places by groups. But a different way to ask that question is, like, do different demographics live in places that are becoming riskier over time relative to the average? And I think that that's something that you could explore in your paper that would be really interesting to see. And then similarly, sort of you show so you sort of said that, there is differential exposure across demographic groups to hurricane risk. I think that you were measuring that based on sort of like exposure to average wind speeds over the panel period. It would also be interesting to see just like how many exposures people have to certain speed winds and how that differs across demographics. I wanted to see more statistics sort of on differences in baseline incomes and earnings and transfers for exposed and non-exposed groups. And then this isn't really a descriptive thing, but it sort of fit better in this slide than the next slide, which is that I think it'd be interesting to see pre-periods in your, more pre-periods in your dynamic effects figures. I think a couple of suggestions that sort of dig deeper into these like issues of heterogeneous treatment effects and understanding sort of nonlinear marginal damage functions. One thing that you could do with your data that I think would be really exciting is you could re-estimate your group-specific dynamic effects at different levels of exposure to wind speeds. So you could sort of re-estimate these for 50-mile-an-hour winds, 90-mile, 110, et cetera. And that would allow you to trace out more of those nonlinear curves by group to really sort of understand what's driving differences across groups and sort of how should we think about addressing those inequalities. And then I really appreciate the point that you make about sort of the importance of moving to a person-based rather than a place-based understanding of inequality. But I want to push you to not drop the place component entirely. And in particular, I think it's sort of really important to understand whether disparate consequences conditional on exposure are due to some characteristics of neighborhoods that sort of disproportionately Black or low income or Hispanic households live in, or whether they're due to sort of differences in households' ability to get support or recover afterwards. So just to be a little bit more explicit about this, we know, for example, that Black and low income households are more likely to live in like low-lying flood-prone neighborhoods. Maybe those neighborhoods are investing in levees that are breaking or not investing in levees at all. And so how much of these differences that you're seeing are driven by those sort of place-based differences versus the differences that arise from sort of insurance that comes after the fact. Okay, so those are, I think, the sort of main comments that I have for this paper, and then sort of moving on to thinking about sort of the green transition to try to mitigate future climate damages and make this hurricane question a little bit less relevant as we move forward. So there's sort of been this longstanding tension between the environmental movement and the labor movement, where workers in the fossil fuel industry have been worried about losing good jobs, have been worried about green jobs not being as good or not having access to those jobs as they sort of become available. And I think, the two movements have been sort of coming together over time and starting to see more eye to eye, which is perhaps well demonstrated by this little bit from the White House IRA fact sheet, which really emphasizes the importance of labor in the climate policy. So, Biden says the Inflation Reduction Act creates good paying union jobs. The law includes some of the strongest labor protections and incentives ever attached to clean energy tax and credit programs. But of course, understanding, what these green jobs are and whether they're going to be good and who's going to have access to them is an empirical question. And as Mark was saying, there's sort of a big challenge to identifying these jobs, and that they span a lot of industries and occupations. They're a relatively new category, and there's not like a single standardized way to identify these green jobs in surveys that we typically use for studying labor and employment. And so, this paper takes that challenge really seriously, again, by bringing to bear awesome new data on the question and using data on job postings, searching those postings for specific words and creating sort of a classification for green jobs, and then sort of using that data to show some descriptive evidence on what these jobs are and how they stack up. I will again not summarize the main results, but sort of my suggestions, again, I begin with just like, I want to see more descriptive statistics again, because this is new data that's really exciting. And I think the theme of all of these bullets is basically like, how are some of these statistics that you're showing us about solar and wind jobs, how do they compare to fossil fuel jobs? How do they compare to jobs in other industries? So for example, at the end of the paper, you talk about how there's a very uneven distribution of green jobs. Enrico Moretti and others have also talked about how there's an uneven distribution spatially of other high-paying jobs, and I just want to have a little bit of a sense of how much more unequal we're talking about. I think that would be really helpful. I also think, it's really interesting to see the occupational wage premia for green jobs versus non-green jobs, but I would also just be interested in seeing how the raw wages posted compare to the raw wages posted in other industries and sectors. So yeah, I think exploring things along those dimensions would be interesting. A second set of comments that I have are sort of related to your definition of what a green job is and what a good job is. So because sort of one of the main contributions of this paper is defining this classification for green jobs, I kind of want like more sensitivity analyses, and you observe occupations in your data, and so how much better are you doing than if you were trying to infer what green jobs were based on occupations? Like how much do the results change? I think that would be really interesting to see. And then your definition of green job is fairly narrow, which is, I think, totally fine for this paper. Like you're looking at solar and wind jobs, and solar and wind jobs are interesting to look at in and of themselves. And I think that that's very reasonable. I think even sort of within the solar and wind category, there's a lot of jobs that are really complementary that you might be missing. So like solar and wind are intermittent resources. And so in order for them to really penetrate the electric grid, you also need improvements in battery and storage technologies. Smart grid technologies are really related. As we discussed in previous papers, transmission and distribution are going to be really important. And so I'm wondering if there's any way to bring in some of these other complementary skills, even in a solar and wind focused paper. But then of course, you could also expand your definition of green job out into energy efficiency jobs or EV and green manufacturing jobs or conservation jobs. And that sort of might be way down the line in the research agenda, but just something to think about. And I think it would have like potentially, it could meaningfully impact some of your results on like the correlation between where green jobs are and manufacturing jobs are, for example. And so that would be sort of interesting to explore. And then just in terms of like what makes a good job, I think, the focus in this paper has been in measuring differences in wages, but differences in job stability and union protections are sort of, I think, a big factor here also. Like part of the reason that fossil fuel jobs are perceived as good is because of high unionization rates. And so if there's anything that you can look at to sort of say something about the union characteristics or the job stability associated with these green jobs, that would be very interesting. And then just one final comment for sort of where to take this paper next. There's a little bit of tension in my discussion because, one of the takeaways from the previous papers was that using these like place measures misses a lot of the distributional impacts more locally, and it's sort of not a perfect measure. And obviously this paper, you don't have employee linkages yet, so you can't sort of perfectly understand who's getting the green jobs. But I think that there's a little bit that you can do I think you can like leverage geographic variation in these different resources to try to understand a little bit more about what jobs the green jobs are displacing. In particular, there's sort of two versions of this that I was thinking about. So this is a map that shows, fossil fuel shale plays across the US. And so as with solar and wind jobs, there's sort of geographic natural resource constraints to where these jobs are located. And, you showed that like solar jobs are primarily in the Southeast and wind jobs are primarily up and down the middle of the country. But then there's going to be parts of the country where there are fossil fuel resources, but not good wind and solar resources, and also vice versa, where there are good wind and solar resources and not fossil fuel resources. And I'm wondering if you can take advantage of that to, for example, look at places that have fossil fuel resources and compare aggregate employment and decline in the fossil fuel sector in places that also then have good renewable resources versus not. And the converse of that, like look at aggregate employment in green job commuting zones, comparing ones that have good fossil fuel resources versus not. And so I think basically like both of these papers, I think are super exciting data settings, and the authors have shown like a lot of interesting results so far. And I think there's just a lot more that you can explore in both. And I will stop there.
Thank you so much, Eva. That concludes our formal presentations. As a reminder, if you do have any questions for any of the presenters, please feel free to drop it in the Q&A box and share your name and affiliation. But first, as I promised, wanted to turn it back to Greg and following Greg, Conor, to see if y'all have any responses to your discussant, Derek's remarks. And then I'll do the same for the last two presenters as well.
All right, so I'll try to go quick. First of all, Derek, thank you very much for the incredibly thoughtful comments. I think they're going to improve the paper considerably. Let me just quickly go through a couple of things. You make an interesting point about manufacturing. Maybe we could chat about this more offline, but my reading of literature is that manufacturing in developed economies tend to be pretty well insulated, but not as much manufacturing in developing economies. So if you were to move this model to a developing country setting, which I think would be interesting, you definitely want to have those damages. But I think in the US, as a first approximation, the no manufacturing damages will make sense. Again, context specific. You make a very interesting point about growth versus level effects, and kind of which is more consistent with what we're seeing. Let me put in a completely shameless plug that Steffi and I, along with Ethan Good at the San Francisco Fed, recently have a paper on growth versus level effects, and we find that there's sort of temporary growth effects and then the long run level effects. And that's, I think, exactly what we would get here in this paper. So you have a hit to investment. That's going to slow your investment down for several periods, like a one-time change in temperature, but it's not going to affect your steady state growth rate. Right. So I think what we're going to see here is temporary but not permanent growth effects. I have no sense of, without doing the analysis of how the magnitudes line up, and I thought your suggestion there made a lot of sense. We can compare these to the existing approaches and see where it comes down, and then also to kind of then say which, if any, aggregate damage function is a decent approximation to the disaggregated. So I appreciate those comments greatly. The other point I have here is about social cost. Yeah, we could definitely do that. The mechanics of the model make it difficult to have endogenous energy use without greatly complicating the solution method, but we could probably get at that with some sort of dice-like approximations of emissions per unit of output and how that changes over time. And then finally, the last thing I had here was what is the role of R&D? I think that's a great question. So if R&D can kind of be a substitute, then maybe we're overstating growth effects, but to the extent that we have changes in capital stock affect your ability to do R&D, then the effects would be magnified. I don't have a great sense either way, which way that goes, but I think it's a great point and one that we can definitely look into. So thanks again very much for your thoughtful comments.
Thanks, Greg.
Hi, Derek. Yeah, I'll echo Greg there. That thanks for the fantastic discussion. And you raise a number of great points for us. I agree that, yeah, our value add is really going to be doing the transmission policy, and that's what we're working on right now. So watch this space. The learning by doing rate, I agree. You're absolutely right. Where we're taking the maximal case for learning by doing. We do exactly those bounding exercises you're talking about, thinking about different rates and how sensitive the results are to different rates. It's not in the paper yet, but it will be soon. And as well on the fossil fuel investment, we're doing that as well. So yeah, this base case that we're talking about where it's no fossil fuel investment, obviously this is the extreme case and we're thinking about modifications to that. Intermittency, I agree, we're pretty weak on at the moment. So I'm really looking forward to reading your suggestions on how to tackle that. Thanks.
Thanks so much, Conor. And to the second set of folks, Jonathan and Mark. Jonathan, I'll pass it on to you in case you have any responses.
Yeah, thanks, Eva, for your discussion. That was really great and very helpful. Yeah, I think, understanding the framing of understanding heterogeneous marginal damages as being a hard problem, but one that I think we can make in this paper make substantial progress on in this paper, I think is really nice. I particularly like the idea of decomposing the distributional effects into the within versus between kind of considerations. I mean, one of the nice considerations you had, the nice Shangatal plots, right, is that we can look at the effects of different individuals exposed in the same place. And so that sort of helps on the one thing, on one margin of it. We can also explore non-linearities, but this within versus between is particularly interesting in terms of trying to dig into more deeply the mechanisms as to why we see these heterogeneous effects. I mean, one thing that stands out is that we don't see increases in transfers for Hispanic populations, which is to suggest that there may be issues of access or other margins that we need to better understand there. But also the descriptors, we can do so much here, and particularly we're doing projects looking at experience as well. So we can see people's experience to hurricanes over the life cycle. And so one interesting question to explore is understand learning from experience. So do we see the experience of exposure reduces damages or exacerbates damages the next time around? So that's another margin to dig into more too. So yeah, thanks so much for your thoughts.
Yes, seconding Jonathan. Thank you, Eva. I loved your comments. I loved a number of the ideas. So the idea of comparing green job growth to other places where you've seen large growth, I think that's super interesting. So Otter and Asimoglu and some people have been looking at the growth of AI jobs using burning glass data. We could do some similar stuff to that, like actually just seeing how the growth of green jobs compares to the growth that they've observed in other situations like that. And you're right, we are, I kind of understate this in what we do, but we are super narrow in our definition of green energy jobs. And we really wavered back and forth on this and decided that we would kind of play it safe in some sense. We feel like nobody's going to be able to argue with us if if you actually include solar or wind in either the job description or the job title, right? I mean, it's pretty clear that's it. But I mean, you're absolutely right? I mean, there's way more jobs than this that I think most reasonable people would define as being solar and wind jobs that we are not capturing here. Not to mention other types of green jobs like you mentioned with energy efficiency. So I think that's a place that we've gone. So you actually mentioned the BLS Green Jobs Report. So there's some interesting history there. They got into the reason why that program got shut down, as I understand it, is that they attempted to have a very broad measure of green jobs, and some congressmen dragged the head of the BLS up in front of Congress and quizzed him on each of the specific type of green jobs that they had defined. So we were kind of scared to go in that direction, and I think in doing so, we were playing it very safe, probably more than we perhaps should have. So great comments. I love the idea about good jobs as well, thinking about whether or not these are good jobs. So I'll stop there. Thank you, Eva.
Thanks so much. So we are close to out of time, but before we close out, just wanted to give an opportunity for each presenter to provide some concluding thoughts to a question I'd like to ask. So I'd love for each presenter to share either a key opportunity for future research related to their research or the field in general, if they want to go wild, and or as an organization that seeks to translate research for policymaking, especially given my role as a policy director, I'm constantly thinking about that. A key takeaway you'd want the policymaker community and our public to have from your research. We'll start from the top again. Greg.
So I think a key takeaway from our research is that kind of standard approaches to estimating the impact of climate change in the US probably understate the long run impacts that climate change will have on economic growth, in part because they don't pay enough attention to the construction sector, and more research on that sector would be very beneficial. Thanks again.
Feel free, Conor, take it away.
Oh, yeah. So I just want to say, I think we're at a really exciting time for research on the renewable energy transition. And I think part of the takeaway from our research is that we can have large benefits from the bills that have just been passed, but we need to think a bit more carefully about targeting these subsidies. And I think a future avenue for research and to take really seriously is how do we optimize grid investment to take advantage of the renewable transition.
Thanks, Conor. Jonathan?
Yeah, I mean, so our research, most broadly, we're really focused on trying to understand the distribution of environmental risk and its consequences. And we think this is particularly important because in light of disparities as well as distributional effects, environmental quality does play an important role in shaping economic outcomes and opportunity. And so that feeds into broader economic disparities as well. So it's important to understand the contribution of environmental inequality to economic inequality.
So I'll quickly say too, so I think number one, when green jobs are located in a particular area, what is the causal effect of that on a community? Can we measure kind of job multipliers, getting back to the Enrico Moretti ideas? And then the second is, when you have a job, what role does that play in shaping your opinion of climate change in general and your support of policies for particular climate change? I think that's a big thing to think about when we think about the political economy issues of this.
Great. Thank you so much, Mark, for taking us home with that. And thank you to all the presenters and discussants. A really important topic, as I think it's one of the existential crises of our time, and really important, impactful research. And looking forward to continuing to engage to figure out how to advance your research and, as I mentioned, translate it for policymakers. And with that, we will close out. Have a great Monday, rest of your afternoon and evening, y'all. Take care.